afternoon, sir. Today, we'll be presenting our presentation on multi-objective A-star algorithm, a powerful tool for addressing optimization problems with multiple, often conflicting objectives. But before we begin, let me introduce our team. We have four members presenting different aspects of the multi-objective A-star algorithm. Ayush will explain the structure of the algorithm and its steps. Shubhankar will discuss the difference between MOA star and A star and the advantages of MOA star. Pranshu will cover the application domains, research gaps, and performance consideration. And I, Yash Rajput, will start with the introduction, the history of MOA A star, and why we need this algorithm in real world scenarios. Now, let's begin by understanding what the multi-objective A-star algorithm is. The multi-objective A-star algorithm, or MOA A-star, is an extension of the traditional A-star search algorithm. While A-star is commonly used to find the shortest path in a graph, it only optimizes a single objective, such as distance or time. However, in real-world problems, we often have multiple conflicting objectives. For example, in transportation, we don't just want the shortest route, but we also need to consider the fuel efficiency, traffic conditions, and the toll costs. This is where MOA star comes in. It optimizes multiple objectives simultaneously rather than just one. To achieve this, MOA star introduces the concept of Pareto front solutions. Instead of giving a single best path, it provides a set of optimal solutions, each representing a different balance between the objectives. A solution is called a Pareto optimal if no other solution is strictly better in all aspects, meaning that improving one objective always comes at the cost of another. Now let's discuss why MOA star is necessary. Many real-world problems cannot be solved using A-star single optimization criteria. Here are some key reasons why MOA A-star is crucial. Real-world complexity. In real life, many problems involve multi-objectives. For example, in urban planning, authorities must balance the cost, environmental impact, and social benefits. In robot navigation, we need to optimize for speed, energy efficiency, and safety. In network routing, factors like latency, bandwidth, and reliability must be considered. Second is trade-off analysis. MOA star allows decision makers to explore the trade-offs between different objectives. For example, in engineering design, choosing between cost and durability is a common trade-off. MOA star provides multiple optimal solutions, allowing for a well-informed decision. Now moving on to the next point, flexibility in problem solving. Unlike traditional algorithms that focus on a single goal, MOA star adapts to the changing priorities. If new objectives are introduced, like a new environmental regulation in city planning, the algorithm can incorporate them without needing a complete redesign. Now, let's take a look at historical development of MOA star. Early foundations from 1980 to 1990. Stewart and White in 1991 introduced the first version of MOA star, extending A star to handle multiple objectives. Their work established the concept of maintaining sets of non-dominated solutions at each search node. Now, moving further, path-based approaches in 2000s. In 2003, Refinidis and Vellhavis introduced MOA A-star, which focused on the path-based expansion instead of node-based expansion. This made the algorithm more efficient. Now moving further, we have recent advancements, which currently are from 2010s and present. In 2015, this Lexco, a variation of MOA star that used lexicographic ordering to prioritize certain objectives, was introduced. This made MOA star even more efficient for problems where some objectives are clearly more important than others. With this background, now we understand that what MOA star is, why it is needed, and how it has evolved over the time.
Hi, in this slide I will be talking about the traditional A-star algorithm and its objective function. The traditional A-star algorithm is a widely used search algorithm in pathfinding and graph traversal. It is popular in AI, robotics, and game development because it efficiently finds the shortest path from a starting point to a goal. A-star algorithm works by evaluating nodes using a cost function, which is f of n equals to g of n plus h of n, where g of n is the cost from the start node to the node n, and h of n is the heuristic estimate of the cost from node n to the goal. The algorithm expands nodes with the lowest f of n, balancing actual cost and estimated future cost. Now, the effectiveness of A-star algorithm depends on the heuristic function h of n. If h of n is admissible and consistent monotonic. Admissible means it never overestimates the actual cost, ensuring optimality, and consistency, that is monotonic. It means that it satisfies h of n less than equals to c of n comma n plus h of m, where c of n comma m is the cost from reaching uh, node m from node n, and h of m is the heuristic. Now in the next slide I will be talking about the key differences between the traditional A star and the multi-objective A star. In the traditional A star algorithm, we do have only one heuristic, but in case of multi-objective A star algorithm, we have multiple different cost functions simultaneously. Instead of a single f of n, it evaluates multiple criteria and finds a set of optimal solution known as Pareto front, where no solution is strictly better in all objectives. Whereas in traditional A star algorithm, it focuses on a single objective, minimizing the total past cost. However, real world problems often involve multiple objectives, such as minimizing both time and energy. Now, in the next slide, I will be talking about the advantages of multi-objective A-star algorithm. There are different types of various advantages of multi-objective A-star algorithm. Some includes the diversity in behaviors. The multi-objective A-star algorithm produces a more varied set of behaviors by exploring multiple trade-offs among objectives. This increased diversity can be beneficial in better problem handling, which includes the better handling of problems where many interesting paths may reach the same node. And the next one is the diverse Pareto optimal solutions, the ability to find a diverse set of Pareto optimal solutions in a single run. Pareto optimal can be defined as a solution is means in a multi-objective optimization, a solution is considered Pareto optimal if it cannot be improved in any objective without degrading at least one other objective.
Now we will see algorithm structure and algorithm steps for multi-objective A-star algorithm. In algorithm structure, we see that we create an acyclic search graph which is rooted at the start node. We also initialize an open list which will contain all the nodes that needs to be explored. From this open list, we will select a node with a non-dominated path. A path is said to be a non-dominated path if there exists no other path which can improve all the objectives simultaneously. If the selected node is a goal node, we will store it as a solution. Otherwise, we will expand that node for its successors. We will keep updating the open list and the closed list, and we'll keep repeating it until open list becomes empty. These are the algorithm steps for multi-objective A-star algorithm. In this first step, we initialize an open list with a start node with zero cost vector and an empty closed list. In the second step, we enter into the main loop, which is the driver code of this algorithm. The entry condition is if open list is empty or not. If open list is not empty, we enter into the loop and we select at the first step we select a node with a non-dominated path with best f value vector. If n is a goal node, we will record it as a solution. Otherwise, we will explore the node n for all its successors s. We move n from open to closed list. Now, after expanding node n, we will see it for all its successors. we compute g value of each s by adding the cost from n to s to the g value of original n. Now we will compute f value of s by adding z value of s with h value of s, where h is the vector of admissible heuristics. It is sum total of all heuristic in such a way that it gives a weighted average of all the heuristic of all the objectives. If S is not in open or closed, we add it to the open list. If S is already in open or closed, update its cost vectors if new path is non-dominated. Upon updating the open and closed list, we remove the no dominated paths from the open and closed list. If all paths to a node in closed become a dominated, we move it back to the open list. After the loop has terminated, which means open list has become empty, we will return the set of non-dominated goals as a Pareto optimal solution. A solution is said to be Pareto optimal in which we cannot further improve a objective until unless we make other objective worse. These are the key components of the algorithm and its structure. There is a set in which we will store all the goal nodes and where cost vector is added to the solution cost. We will store in the open list in the form of n, vector g and f, where n is the node, vector g is the cost vector, and f is the set of all non-dominated f values. These are different algorithmic approaches for multi-objective A-star algorithm. The node-based approach is the original multi-objective A-star approach. It maintains a set of non-dominated paths at each node while expanding nodes with promising cost vector. The second approach is path-based approach in which two algorithms come: non-dominated A-star with path-based optimization and a second algorithm lexicographical goal ordering A-star. In this, the selection and expansion of non-dominated paths is taken into place rather than nodes. It typically shows better memory efficiency. The third approach is a hybrid approach in which two algorithms come. The first one is two-phase path planning with local search, and second one is a improvement on the non-object non-dominated path of based optimization with decision rules. It combines multi-objective A-star with other techniques like local search or dominance relationship to improve performance.
The multi-objective algorithms have been widely applied across the various domains, solving complex optimization problems efficiently. Let's explore our key areas. Robotics and autonomous systems. In robotics, the MOA star helps in path planning and by optimizing energy, time, and safety constraints, making autonomous navigation more efficiently. Further, the transportations and network. For the transportations, these algorithms enable smart routing planning by considering distance, time, cost, and even environment impact. For the third one, the VNSI design. In VNSI design, the multi-objective A-star algorithm plays a crucial role in layout optimization, ensuring efficient electrical and physical constraint management. The last one is the resource allocation. And in resource allocation, it balances competing demands to optimize resource distribution effectively. From robotics to optimization, the MOA star is shaping the future of intelligent decision making. When working with MOA star algorithm, it's essential to consider their performance implementations. Let's go over the four key points. The first one is the computational resources. The MOA star algorithm generally requires more efficient resource than the single objective A star algorithm. This means they can be more demanding but more powerful for complex tasks. Memory uses. Path-based approaches tend to use less than node-based approaches, making them a better choices in memory-constrained environments. For the solution growth, as the problem size increases, the number of non-dominated solutions can exponentially increases. This highlights the need for efficient pruning techniques to, to fast up the searching. For the last one is the heuristic design. The heuristic design plays a crucial role in practical performance. A well-designed heuristic can significantly improve efficiency and accuracy. By understanding these factors, we can optimize MOA star implementations for real-world applications. Here, as we have explored the MOA star, it's important to identify the key research gap and future directions. Let's go over the four promising areas of development. The first one is the machine learning algorithm. One major direction is integrated machine learning to develop the problem-specific heuristic. This can improve the efficiency and adaptability in complex scenarios. The second one is parallelization strategy. Next, leveraging modern computing architecture through parallelization can significantly enhance the performance, making MOA star more scalable. The third one is the approximation techniques. For the huge problem spaces, approximation techniques can help manage computation complexity while maintaining solution quality. And the fourth one is the dynamic and online MOA star. Developing dynamic and online MOA star can improve adaptability in changing environments, making real-world decision-making more feasible. By focusing on these areas, we can push boundaries of MOA star research and unlock the new possibilities. And here, I conclude with some references and resources that helps in our work. The first one is the multi-objective ACE star by Bradley S. Stewart and Jenscy White, which provides the fundamental insights into MOA star. Next, a new approach to multi-objective A star by J.L. De Cruz, Lawrence Mando, and Lorenzo Mando explore the alternative strategies for solving multi-objective search problems. Finally, the multi-objective A-star search is consistent heuristic by Jose Luis Perez de Cruz and Lawrence Mando examines the role of heuristic in improving search efficiency. These works offer a valuable perspective and methodologies that contribute to the ongoing advancement in this field. Thank you.